Welcome to SportsSci, where I try bridging exercise science and sports analytics in R. Today is going to be a fairly quick and simple screencast where I go over some functions that we've already seen before, or you can find in the mid-sprint package that I've published that can be found on my Twitter page at Aaron Z. Pearson. In particular, we're going to be looking at the speed and acceleration over time functions, and this is going to help lead us into some new functions that I've been working on for a large package update, or even leading into a newer package that will supersede mid-sprint for researchers in particular, or those who would prefer building their own plots unlike those in mid-sprint, so that there's a little bit more customization that they can or you can use. So we're going to get two outputs. This is going to be the first one. This is something that is seen in the mid-sprint package. So this is just going to be speed and acceleration of a player over time. And then we're going to have a very simple output like this, where we're comparing three athletes, all of which have the same top speed, but have different acceleration abilities. So in this screencast, I'm not going to be live coding because you can physically copy and paste this from the mid-sprint package, which I will add in here. So github.com/Aaron Z. Pearson/midsprint. I believe that is the link that you can find it. Of course, you can find me and my blog, midsprint.io. You can follow me on Twitter, which is the best place to find me, at Aaron Z. Pearson. And my best email address to reach me at is aaron@midsprint.io. So for today, we're going to be using the ggplot2 package for some advanced plotting abilities. And we're going to set the theme, so that way we don't have to include this theme from plot to plot. We set it early on, and that way every plot moving forward has this same theme to it, or same look. So these functions here, speed time and acceleration time, or accel time, are in the package, but we'll go through it step by step here, which we can then build upon. So our function takes three arguments: the player's max speed, the time at which we want to know the speed they're at, and the player tau. And the player tau is the relationship between their speed and acceleration abilities. So typically you'll have something like, and this is just an example, somebody's top speed of 10 meters per second and their top acceleration rate is, let's say, 14 meters per second squared, and your tau will be 0.71. In this screencast, we're going to be looking at players that are a little bit more balanced, which we'll get to later. But for now, we'll work with somebody who's completely balanced. So 10 meters per second and 10 meters per second squared is their tau. So it would just be 10 over 10, which is 1. So these are functions that I also used in my Big Datable submission last year, and it builds those really nice plots. So we take the player's max speed and we multiply it by 1 minus this exponent, or E, you might know it as, this exponential value, and what we get is actually the speed that they're running at a certain time point. So let's run that, and we'll go through an example here. So speed underscore time, we're going to use their max speed of 10. Their split time, let's say we want to know after 3 seconds how fast they're moving, and their player tau is 1. And we see that they have reached 9.5. So this is fairly realistic, especially in something like a 40-yard dash or 100-meter sprint, where by the end of it, by 3-4 seconds, when they're reaching the end of that sprint of that 40-yard dash, they've pretty much reached their max speed. So let's do that again, but we'll do 0.3 seconds. So this is where max acceleration is really high, which we'll see. And you see that the players only reached about 2.6 meters per second, which is fairly fast after a third of a second. So for acceleration over time, let's run this. And this is essentially the inverse of max speed based on their initial ability. So max speed over player tau actually calculates the max acceleration that they're able to reach. So theoretically, this would just be able to be, if we know their max acceleration, we could just put in 10 here, but we'll keep it as this so we can use it for different relationships and different players moving forward. And again, we multiply by this exponential. Just this time you don't have the 1 minus, and again you get their acceleration rate at a given time point. So let's run that again. So accel time, and we'll use the same values. So 10, 3, and 1. And we know that as players reach their top speeds, they have a very limited amount of acceleration that's left in them. So we should see almost 0 here, which is fairly true, 0.5 meters per second squared. So they have a very limited ability to then continue accelerating. Whereas if we have it at 0.3, we'll see that they're at 7.4 meters per second squared. And that makes sense. We're moving at 0.3 seconds. They're only at 2.6 meters per second. So they still have this massive ability to accelerate and reach that top speed. Or let's say in the next 2.7 seconds, they have this huge amount of acceleration ability to reach that 9.5 meters per second. So I took a slightly different approach to building this data set just for just so we can see that, you know, there are multiple ways of doing it. What I did was I built 3 vectors here. So we have the split times or splits, which we will look at. And this is just from 0 seconds to 5 seconds by 0.1. So this really gives us a very nice granular look at the player's abilities, which will then translate very nicely to the plotting or the plots that we're going to look at. We use the speed time function that we've already built. We have their max speed of 10. Splits is that split time that we've seen up here. And their player tau of 1. So when we run that, this has, just for reference, 501 values or numerical values in the vector. So we should see that speed comes out to the same thing, which it does. So we see that at 5 seconds, they've reached 9.93 meters per second. In this case, it's a little bit, it's almost impossible over time to reach this max speed based on this formula, because what we're actually reaching is an upper asymptote. So this is a value that can never be reached, but over time we get just incrementally closer and closer. So it's when you're at 9.93 or you're at 9.89, you've pretty much reached your max speed. We'll do the same thing for accel time. And if we look at accel, we should reach just about 0 at the end. And we have you're accelerating at such a small rate that it really doesn't make a huge difference in the end. If we scroll up to the top here, we should see that at 0 seconds, you're at 10 meters per second squared. And that makes sense. You're starting from a dead start during your 40-yard dash. So you have all the ability in the world to accelerate hard, which then tapers off near the top when you've reached your max speed. So to build this data frame, all I did was I put the split times or split here, speed and accel. I just ran this, and you get this data frame built by these 3 vectors. So that I called athlete_sprint. And here we have it. 501 rows, of these values. Let's scroll to the top here, split. So we see that our time increases by 0.01 for every row, and these speed and acceleration values correspond with the vectors that we just built beforehand. So let's plot this. This is something that you can also do in the MidSprint package. Earlier versions had it in base R, so we'll do it like this. And then the latest update incorporated ggplot2. And that was to help sports scientists automate the report or coaches reporting abilities. So you run it, you save the report, which is a function in there, and then you get, or you return this really nice PDF that can incorporate all of the players that you want. But this one, we're going to do it a little bit more manually. So that way you can really dive into how specific you want it to look, or, you know, if there's anything you want to add or remove from the plot itself. So let's start by plotting it. So this is what we come out to. So here we have the plotting function from base R. We want speed on the y-axis, our split times on the x-axis, and we have to declare which data we're using. So we're using athlete_sprint. Type L. L is for line. If we didn't include that, which let's comment that out. If we don't include that, we get points. But it's just a little bit messier, at least in base R, to use points. So we'll go back to line. Our X label is time in seconds. Our Y label, for simplicity here, I put it all on one row, but you can actually have it where speed is above acceleration or in different colors. That takes a little bit of time and effort to put in, and I encourage you to do it. I just didn't feel like it was necessary for this screencast. So let's go back to there. And then, unlike ggplot2, you don't have this plus sign where you can then add another layer. So we want another line which represents our acceleration rate. So it's the same type of approach where we have acceleration on the y-axis, our split times on the x-axis. We declare our data, and just for visualization, I set the color to red, and this is what we come out to, which is something that we've or should have seen before, is this really nice approach to their speed and acceleration abilities. You can always include a title here, but I find that it's a little bit cleaner in ggplot2 to work things out like that. So this comes out to the exact same plot, just a little bit more advanced in terms of visuals. So right here we have our ggplot function. We declare our data, and then in our aesthetic, we say, okay, we want X on our, split times or splits on our X-axis. So we, as you can see, we haven't declared our Y-axis, and that's because we have two different layers that we're now adding, which are both points or geom point. So in our aesthetic, we have Y equals speed here, whereas geom point, our second layer, has acceleration, which is very similar to what we just saw in the base R plot. So we have speed as our first layer, and then acceleration as our second layer. I've done the same thing here where I've said, okay, black is our speed, red is our acceleration, which was the exact same thing as our base R plot. I explicitly declared the size because I wanted it to be a little bit larger than their general output. And alpha equals 0.5, which means its opacity, or how see-through it is. So that way, when they're a little bit more spread out, we see that they're, when points are a little bit more spread out, we can see them more individually. And when we've reached our top speeds where we're, accelerating at these minimal values, or, our top speed really isn't moving all that much, it'll be a much darker color. So that way we know that the points are a little bit more condensed, or there's not as much change. Our X label is time in seconds. Our Y label is speed and acceleration. I can add in a GG title, and that could be something like player's mechanical speed sprint abilities, and we run that, and this is what we get. So it's the same thing here. It's the exact same thing, just a lot nicer looking. And this is where I was talking about the alpha levels, where they're much bigger jumps in speed and acceleration at the beginning. I'll see if I can improve that there. Yeah, so whereas here there's the much smaller changes in time, and we see that it gets slightly darker. To really exaggerate that, we could change alpha to 0.2 and rerun that. And there we go. So we see that it's, a dark gray here and a darker red. And this is a much more opaque or transparent color. So we really get that understanding of, how much, or the rate of change over time for both sprinting and acceleration. What I then wanted to do is see how different tau values affect their players' abilities to reach that top speed. So I built these two other players. So just for reference here, we have the speed vector that we've already built for player 1, who has a tau value of 1. I did the same thing for a second player, which I called the object, or the vector is now called speed 2. And I said 1.4, which is a top speed or speed dominant athlete. So 1.4 is fairly heavily speed dominant. And then the other player, which I've called speed 3, their speed vector, top speed is the same as the others, but this player is now acceleration dominant. So just to remind us that tau is equal to speed over acceleration. So if somebody is acceleration dominant, I believe I used 14 earlier, they're 0.7, whereas if they're speed dominant, let's go 10 over 8, for example, we'll get 1.25. So 8 would be their max acceleration abilities. And again, I used the same approach of these vectors to build our data frame. So split is our split times. Athlete 1 is speed. Athlete 2 is speed 2. Athlete 3 is speed 3. So if we run these and then we build that, let's take a look at it. Let's go actually look at the top 6. So that way we don't really just see the bottom of it, or bottom of the data set. So here we have our seconds, and we could already see that these athletes, their speed and acceleration, or their speed rather in this case, changes at very different rates. So again, athlete speed 3 is acceleration dominant. So we should see this individual outpacing the others, which we do. This athlete here, athlete 1, is very balanced, and athlete 2 is top speed dominant. So they have limited ability to accelerate, yet their top speed in this case is 10. So again, what we did was declared our data. This one is now athlete underscore sprints underscore compare. X is the same thing. And then all I did was athlete 1, 2, and 3 for their speed values. I declared that they're different colors. Athlete 1 is black. Athlete 2, who is speed dominant or top speed dominant, is red. And blue is our acceleration dominant. And let's change that again to 0.2 for clarity's sake. Here I have the X label as time, Y label is speed. Since we're not plotting acceleration, we don't need that. And then I added in the title already of player speed comparison. And when we run that, we get this. And that's exactly what the output was that I showed you earlier, where blue is acceleration dominant, red is speed dominant, and black is very well balanced between the two. Typically, you won't see something like that. You would see something where somebody who's speed dominant might be a little faster. We'll say 12. 12 is very fast. Usain Bolt, he's reached about 12.5 meters per second. So this person is very highly top speed dominant. Let's say this person is not nearly as fast, so they're at 8. And again, we'll go with this individual, athlete 1, is right in the middle. So 10 meters per second is their top speed. Their tau is 1, which means that their top acceleration rate is also 10. So let's take a look at that. We'll run that again, and we'll see how this comes out. And there we go. So since athlete 3, I believe, is so athlete 2. Since athlete 2 is so top speed dominant, they end up actually outpacing everyone else. But when you're talking about something in like a football context, where our accelerations are like 1 to 2 seconds, well, we see that after a second, the acceleration dominant player, well, he's already almost maxed out his abilities or her abilities, whereas the balanced and top speed athletes are fairly well, they're going toe to toe up until about 1.5 seconds. So you can use this information to better prepare or better understand players' abilities, and potentially better, you could potentially better utilize them in certain positions. So you might want to shift players around based on their acceleration or speed abilities. But that's the gist of it. This is, again, a review of what I've already put out in the mid-sprint package, and that is going to help lead us into these really cool functions, like the speed acceleration relationship, and some other ones that I've been working on, which will be thrown into either the mid-sprint package or this new package I'm working on in the near future, hopefully, where we really get these really cool, really nice relationships that we're building per person and between people to better compare them and help practitioners, sports scientists, rehab practitioners, performance staff really hone in on athletes' weaknesses and strengths and have a much clearer idea of the direction in which they need to prep these athletes. So again, you can check out my blog, which hasn't been updated for a little while. It's at midsprint.io. You can reach out to me on Twitter at Aaron Z. Pearson or by email at aaron@midsprint.io. Again, if you don't have the Midsprint package, I encourage you to download it. This is all automated for you, and it comes with a really nice walkthrough. Super simple. You can get it at github.com/AaronZPearson/midsprint.